All right, gang. So welcome back to the Z-score chapter. This is part two and the last part of the video. So there's not a whole lot left to go over, um, but I felt like the videos are getting too long. So just to break them up is a little better. So it's not monotonous and easier to find your place. So in the last video, we talked about what Z-scores are, how to find a Z-score if you have an X value, and then how to find an X value if you have a Z-score. So now we're going to take it a step further than that, and we're going to look at the z distribution and the standard normal curve, two names describing the same distribution, right? And how we can use that to figure out a proportion of scores under the curve, right? And so let's take a look at that. I'm going to share my PowerPoint with you, and so we'll pick up right where we left off if you're following along on the PowerPoint. So here we are, right? We are looking at the standard normal curve, and you don't have to write all these numbers down. Like, don't do that. Don't waste your time. But if we take a perfectly normal curve, right? Remember, that's the z curve. It's like absolutely symmetrical, right? That's why it's called a standard curve. It's standardized, so it's a perfect normal curve. Then these numbers here that are on this graph, the numbers that are on the x-axis, you see all those 0.3413, 0.1359, and so on, right? Those are standard numbers too if you have a perfect curve. Now, those numbers represent what proportion of scores are in those segments underneath the curve. So let's take a look at those. If we look at the numbers going from just 0 to +1 on the x-axis down here, you get a 0.3413. So that means that is proportionally, if this whole curve adds up to 100% of the scores, in just this little sliver, right here, we get 0.3413 of the scores, or roughly 34% of the scores fall within, this range right here. And then we could say that's between 0 and +1. That because it's symmetrical, it's going to be the same number if we go the other way. So if we go from 0 to -1 or 0 to -1, so one standard deviation below the mean, then this is the same amount of space. It's just on the left side of the mean as compared to the right. So the number is going to be the same, 0.3413, proportion of scores, or roughly 34% of the scores. So that's why earlier when I kept bringing up that 68% number, I'm combining these two segments together to get that number. So here's where all the majority of scores, what we call a typical score, lie. They're roughly 68%. It's like 68.26%. That's harder to remember than 68%, right? So I'm giving you an estimate there. Now we can look out further and see how rare the scores are. There are fewer of them, lower frequency of scores between one standard deviation and two standard deviations, right? So over here we're looking at roughly 14% of scores, 0.1359 proportion of scores, or, about 14% of the scores between 1 and 2. So not very many, right? And if we go further, like remember, well, we'll look at this in a second. If we go like between 2 and 3, now we're looking at like 2% of scores. So very, very low frequency. And you go beyond 3, we're looking at less than 1% of scores fall within that range. So beyond 3 standard deviations, there's almost no data out there for this distribution. There is data though. So we should say that it might be one score, but there it is. It exists, right? So the handy thing about the Z distribution is that because it's perfectly standardized, if you know a z-score, then you can use that as a marker, with on this curve itself, and you can ask questions like, what's the probability of, or the proportion of scores that are this exact score? But you could also say, what's the proportion of scores that are at this score or below it, or at this score and above it? So for example, if we look at this distribution and I said, well, how many scores are there below a standard deviation of +1, right? So how many scores are below one standard deviation above the mean? So, okay, well, here's one standard deviation above the mean, right? Drew my little line in the sand here. Then how many scores are below that? Well, I just add all these together. I add all these proportions to the left, add them all up. So you can make this really easy on yourself because you know, okay, well, this is half the distribution. So that would be 50% or zero point 0.5 scores, 0.50. So if I add 0.50 to 0.3413, I get 0.8413. So I could say, well, it's roughly 84% of all the scores, or 0.8413 proportions, right? Now, same thing if I went the other way. If I said, all right, well, how many scores are above one standard deviation above the mean? So then I'm just looking to the right. So I go, well, here's one standard deviation above the mean. So I'm saying above that. How many scores are above that? Well, I'm just going to add up all of this information here, right? So I would take 0.1359 plus 1 plus 0.0215 plus 0.0013, add all those up, and that'll give me, the amount of scores above 1. What's handy, since this is all standardized, you don't have to do that math by hand, since those numbers don't change, right? That's what it means to be standardized. These numbers are fixed, essentially, if you have a perfectly symmetrical distribution. So what's good about that is that we can use a table, and you have a table in the back of your textbook that can help you out with this. So that table, and let me pull mine up here. I'm going to grab my book, is on 2 pages, page 351 to 352. In the back of your book, it's Appendix C, Table C1, right? So pause the video, grab your book, or if you have the ebook, go to your ebook and look up the Z table. And I'm doing the same. I'm going to grab mine. I got my book here. And I'm going to switch now to my document cam, and we're going to find some probabilities associated with those scores for Slug, Binky, and Biff. And I'm going to show you how to use this table. So let me switch to my whiteboard cam. There we go. All right. So here are the scores we have for Slug, Binky, and Biff, right? We got the Z scores already. Negative 1.67, plus 0.33, plus 2. So let's do something with these 3 Z scores using the table now. So I'm going to open up to page 351 in my book. It looks like this. Appendix C. Be a little hard to read on my document camera here. So definitely get your book out and follow along. I think it'll make more sense. And let's just take one of these scores. Let's look at Biff's score. So Biff has a score of 2 standard deviations above the mean, right? Okay, so if I have a question like, well, how many scores are, oops, I told you guys the wrong page number. Shoot, I'll have to fix that. The page number is not 351. That's a totally different table. I was confused for a second there. It's going to be page 347. Sorry about that for the Z table. So page 347 through page 349. That's the table you want to use. That was throwing me off. Okay, so if we look at the Z score table, you'll see in the blue columns, right? This is where you have the Z score itself. So let's find a Z score of 2.00. We're going to have to turn the page until we get to page 348 over here in column A. And we're going to go down to 2. Right, so we got a 2 there. And if you look to the right, it says body or tail. So we go, okay, well, the body is how many of the scores are between the mean and 2? 0.9772. So let's look at that for a sec. All right, 0.9772. We're talking about a lot of this distribution. We draw a new one without all this unnecessary info, right? So if this is a +2 here, and we're saying we want all the scores that are to the left of that 2, that's the body, right? So here's the body of the distribution. Well, that makes sense that it's so high. It's 0.9772. That's our proportion, or roughly, 98% of the scores. But that makes sense because this score is so high. It's way over here on the right that almost all the scores, like 98% of them, are to the left, right? Now look back at that table again and look at that score of 2. And look in the tail, it says 0.0228. All right, so if we look, this direction, then our P equals 0.0228, or, roughly 2% of the scores, which is not very many because after all, it's just this little teeny area, right? Compared to this like 98% of scores on this side. So that's what the Z table does for you. It breaks it up into, body and tail. And that's really handy because of this distribution being standardized, those numbers don't really move. So you can always figure out, what proportion of scores are there that are related to each Z-score. And we can do the same thing for, let's practice it just for practice. Let's look at Binky next. So I'm going to erase this slug info, this BIF info here. And let's look at Binky now. So here's Binky's info up on top. So I'm just going to redraw the distribution down here without all of this excess. So we've got Binky here with somewhere around here, plus 0.33. So let's do the same thing now. Go back to your tables, and we're going to look up a 0.33. And we're going to have to start on the first page here on 347. And in the blue columns where it says Z-score, look up a 0.33. And it looks like we got it like right here in the middle of the second column. And it has body and tail again. So for the body, it says it's a 0.6293. So that's referring to all the scores to the left. This is a 0.6293, right? So our P equals 0.6293, or roughly like 63% of the scores. So if we go the other way, you could probably do that in your head, right? 62%, what's left, right? But let's use the table for practice. We go to 0.33 and look over in our column C for the tail, and it says 0.3707. So I forgot what it said, 3707. Right? So that's talking about all the scores that are to the right of that Z-score, right? All the scores over here. So in this case, this is the tail, even though it's big, and this is the body. And we can use this Z table to figure out those numbers. This is also really handy in terms of thinking about probability. And that's how we're going to use it for the future, in chapters coming up. So while this P right here, if you leave it, in this decimal form, is really how you report probability, and then proportions, probably better actually to report percentages, like to say, okay, this is roughly, 63% of the scores. And so that means this is 37% of the scores, right? To the right or to the left, or in the tail and the body. But it's also a probability. So if you said, just at random by chance, if you could have all of these scores that are in this distribution, imagine them all sitting in one big pot, right? Or one big jar. And you would like to shake it up so it's random. And then you reach in and grab one. What's the percentage, or what's the probability rather, that you would get a score greater than 0.33? You'd say 0.3707. Right? So it's kind of the same process for figuring out probability as it is proportion under the curve. We just have, different terminology and different situations in which you might use those. Okay, so you will have to get your book out, and if you use your book to solve a few questions about percentages or proportions of scores relative to a Z-score. So you'll get some practice with that. It's not a whole lot, right? But it will be a whole lot. I mean, it's not that difficult, but it will be an important part of our course as we move on. Okay. Now there's a couple other things left for this chapter, so let's review those two while we're here. right, let's go back to my PowerPoint, and I'll change this number. This is wrong, so I'll have to fix that on the PowerPoint. Whoops. All right. So now we're going to look at distributions that are made of sample means instead of just individual scores. So in the previous example, we were looking at Slug, Binky, and Biff. And so we're just looking at a distribution that's made up of scores from individual people, right? So Slug, Binky, and Biff weren't the only people in that study. It's just the three that we were looking at. But we're taking one score from each person, and we're just creating, one population out of those scores, or creating a sample out of those scores, but one data set, right? But what happens if you're using you're dealing with sample averages instead of a population, right? And so you want to use a sample to make an estimate about your population. Like, what do you do, right? Well, part of that involves using something called the distribution of sample means. And so let me give you this god awful definition. I realize it's god awful. You can write this down if you want, but I don't even recommend it. I put this up here because it makes me laugh, because it makes no sense to people that don't already understand statistics, right? Don't get me started on bad and poorly written statistics books, but this is a good example. So let me read it to you. This sampling distribution of means is a distribution which shows all possible sample means that occur when an infinite number of samples of the same size, n, are randomly selected from one raw score population. It's called the sampling distribution of means. So that makes sense to me, but then I've been using stats for a long time. So let me give you an example of what that's talking about. And it's related to this next idea called the central limit theorem, right? And I'll explain both of these to you on my whiteboard in just a sec. So the basic idea is that, okay, we're using averages now to make a bell curve instead of using X's to make a bell curve. So the X's are an individual score. Average, right? That's a descriptive for a group of individuals. So it's kind of like you're expanding the idea out, right? You start with one group and you get an average. And then you take that average from group A, but you did the same thing for group B, for group C, for group D. So you have these 4 different averages from all 4 of those groups. You do that enough, then you have a collection of averages and you can put them together to create a distribution. And so there's some theories about this, and one of them is the central limit theorem. It tells us something about the sampling distribution of means. So it says here, if you're going to get an approximately normal distribution, right? If you have enough of these samples, you get a normal distribution, and the average from your sampling distribution, should be equal to the underlying raw score population, right? So the idea there is that if you just take the averages from all of these different groups and put them together, it'll look like, you measured everybody that you want your study to apply to, right? And the same thing with the standard deviation. It should be related to the underlying raw score. So let me give you, before we get to the formulas for that, and the formulas are not tough, but before we get to the formulas, let me show you just kind of an example of what this means. Let me give you an example of it. So let's go back to my whiteboard here. Okay, now let's say, you know what? This is a good example. I was talking about standardized testing at the beginning of the last video. So if we take that example with, like, say, a whole high school district, right? Let's take the Kern High School District. There's a lot of schools. I forget how many there are, but we have a big high school district here in Kern County, right? Let's just take one of those schools. So let's say that we're using some standardized test, and maybe it's like a verbal reasoning test or something like that. And maybe we go to, I went to high school here in Bakersfield. I went to East High. So I'm going to put EBHS here, right? So let's say we're looking at just East, and we give all the juniors at East the same test. Well, we know that their scores are going to be kind of all over the place, right? Some students are going to score better than other students, but most of them are going to be somewhere in the middle and create an average for us, right? So we could get a bell curve from this school. And, we have all these different X values down here on our x-axis because some students score better than others, just the way it goes, right? And then there's going to be an average right in the center, and that will give us our x bar, right? That gives us our mean just for that school. So the point is that this distribution is made up from scores from individuals, right? Individual students. Now, if we take like the whole Kern High School district and we want to create like a mega distribution, that means that, you know, we've done this at every high school in the district. And I don't have space to put all of them down here because there's so darn many, right? Well, we're still going to get a normal distribution because some scores, you know, as a collective are going to outperform, you know, other schools. I think I said that wrong. Some schools are going to outperform other schools, right? Just as like a group. So maybe in the middle, like this is our average score. Maybe that's right where, you know, EBHS falls. But other schools are going to outperform them, right? They're going to have a higher average, right? So here's our average for East, right? And it matches the average for all the schools put together. But maybe this one comes from like, let's do the directions. We got East, let's do West. So maybe this is West High, right? They performed a little better. And then maybe South performs a little better than West. I don't know. I'm just making this up, by the way. I'm not trying to show any favoritism. I'm just the directions as they come to me. And then we have maybe North is further to the right. But now these are not individuals' scores, right? These are made up of a collective, right? They're made up of averages instead of individuals. So that's the idea with the sampling distribution of means. So I could go the other way too. So some scores will underperform comparatively. I don't know. Let's say, you know, this one is just, I don't know, make it up. Who else do we have? There's Stockdale High School, right? What is theirs? That's South. Is it? I have no clue. So let's not use them. Let's say it's like, oh, Ridgeview. Okay, Ridgeview High School and so on, right? So you get the idea that what we're trying to do is figure out what proportion of averages, you know, differ from the average for all of them put together. It's the same concept, just inflated here, dealing with groups, you know, in their average instead of just individuals in their averages. But it's the same idea. It changes the math a little bit because we are doing, you know, kind of an estimate now. We want to find out, in this case, you know, how much variance you get, you know. I guess I would say when you have a randomly selected sample, the average difference between the sample means and the population mean. So it's the same idea, because we could say the same thing, that standard deviation is, you know, when you've randomly selected individuals, you know, it's the average difference between the sample, between the score and the sample mean. In this case, it's just for a bigger group. So we would say when we've randomly selected samples, the average it's the average difference between the sample mean and the population mean. It's like how much variance you would randomly get from a population of this size. That's really what like sampling error is all about. And that's like our first thing we're going to look at here back into the PowerPoint. It means we need like a different calculation of standard deviation, essentially. But it's very, very similar in concept. It's like, what's the average distance from the center when you're dealing with average scores instead of individual scores? So it changes our math just a little bit, right? So the first thing we need to do is calculate what's called the standard error of the mean, right? So it's like the standard deviation, but it's for the sampling distribution of means. So it changes our math a little. We have to do two steps now. Instead of like just jumping right into a z-score, right? That's the whole goal of this chapter, right? Is to find z-scores. In this case, first we have to find the standard error of the mean. So I'm going to write this down on my whiteboard. And really, I just want you guys to think of these as like step 1 and step 2, because the goal is to transform a z-score. So first we're going to do standard error of the mean, and then we're going to solve for z. All right, so here's step 1. You can see in this formula, we just take the population standard deviation and divide by the square root of n, right? And you have to have this info to be able to solve it. So the nice thing is you just have to pay close attention to the notation itself. Like there's a difference. We have this not symbol and an X with a bar over it compared to a not symbol with an X with no bar, right? It means different things. So the bar means, oh, we're talking about this standard error of the what? Standard error of the mean, right? And this is the standard deviation of these individual x values. So there's some logic there behind the notation. So we take that standard deviation that we already have access to and divide it by the square root of our total number of scores. And then once we've done that, then we can jump to calculating z itself. So for z, we can take the average. So let's say that's East High. So I was talking about high schools, and we want to turn East High, their average score, into a z-score and compare it to our collection for the whole district. Well, we would want to know, pieces of info to be able to do that, right? We got to know this. This would be East High's average. Then subtract the district average to get a distance, and then divided by the standard error, which is the average distance from the district's middle, right? So let me go to my whiteboard and we can figure something out. So let's see here. Okay, stop sharing. Cool. So here's the idea, right? Here are the formulas, just step 1, step 2. And like I said, you already have access to all this info by the time you get to this point in a problem. So you just have to make sure you plug everything in, into the right place. So, all right, let's say that we know that our standard deviation is 12, right? And our n equals, and how many schools you think we have? I don't remember. Let's say we have like I don't know, 25, right? And then maybe East High's average score is a score of like 76. And then for the entire district put together, so like all the high schools combined, what is the average score? I don't know. Maybe it's, something like, let's just say 70. So you can see here, we already have everything we need to solve, right? So standard deviation goes there, our n goes here, our sample average goes here, and our population average goes there. Whatever answer we get from step 1, we plug in down here. So to solve for this, let's do it one step at a time. So we do the standard error first. In this case, we would take the standard deviation of 12, right? It's right here, 12. And then we divide by the square root of n, which is 25. So it comes down to 12 divided by 5. Do the square root first. And get my calculator out. The danger of using my phone as my calculator is I don't know if any like weird juicy text messages are going to pop up while we're working on our math. I mean, I kind of hope so, but I hope not at the same time. I'm just kidding. I don't get juicy text messages. Okay, so we do 12 divided by 5 equals 2.4. All right. So our standard error is a 2.4. So we would say the average distance from the center of all the high schools combined is 2.4 standard error units, right? It's kind of the same thing as saying 2.4 standard deviations, right? Okay, now step 2, since we have this info, we can plug it in. So for step 2, we're going to solve for z for East High, right? So let's say here's the score for EBHS, and this is for the entire district, right? So we're going to take that EBHS score of 76, and then we're going to subtract that for the entire district score of 70, like that. So we know that's 6, right? That's easy. And then we're going to divide by the standard error that goes down here. So it's like, where does this come from? Well, that's what we just solved, right? So we put our 2.4 down here on the bottom. So we're going to do 6 divided by 2.4. So 6 divided by 2.4 equals 2.5. There you go. So that's all there is to it. We would say in this case, then east is 2.5 standard error units above the mean, which of course I didn't think about these numbers too much ahead of time. That'd be really high if that were the case. Then we'd say, damn, East, what have you guys been doing? How did you get such high scores? Right? Okay. So that's this chapter in a nutshell, and we'll later today or tomorrow morning, I will have the next chapter up and ready for you guys. Hit me up if you have questions, and I hope to see you all soon. All right. Bye.